redirections in group theory and triangulated categories. Our speaker today is Chrysostomos Psaroudakis from the Aristotle University of Thessaloniki, and he will be talking to us about regular triangulated categories.
Thanks. Thanks a lot for the introduction, and thanks a lot for the invitation. So I'm going to switch camera, and so can you see? Let me pin so that I can. Okay.
Yeah, I can see.
Okay. So the title of my talk is Regular Triangulated Categories, and this is joint work with my student Panagiotis, Kostas, and Jorge, Vitoria. Okay. So the talk is based on a paper entitled Regular Triangulated Categories that hopefully soon will be on archive. And the plan for today is hopefully we'll have 4 parts. So first I want to give motivation and explain what is the aim of this talk. So clearly today I want to suggest like a notion, a new notion of regular triangulated categories. This is a new like homological framework for. I mean, we propose a new framework where we can really study various homological properties for triangulated categories. And the idea is to try to define everything that we would like to have for triangulated categories via some certain distinguished subcategories which are intrinsically defined. I will explain what I mean by that. And the main idea that we'll see is the notion of faraway subcategories, faraway orthogonality. I'm going to write orthogonality. And we'll see also a connection with silting theory here. Okay. Then the main part will be about the regularity of triangulated categories. And the last part, we'll discuss some applications, and basically I will discuss some applications on singularity categories. Okay, so this is the plan for today. Okay, so what is the motivation? What we want to do? Can you see what I'm writing? Clear? Is it clear? Okay, thanks.
Yeah.
Okay, motivation. Okay, so there are some well-known implications in homological algebra. So, for instance, if you have a ring, then we know well what means this ring to be of finite global dimension. And when we are in the commutative setup, we also have the classical notion of regularity, right? And we know here we have to be aware that this is always the case, but this implication is not true because we have Nagata's example, right? So, and then we can move further. We have other homological nice characterizations like the ring R being Gorenstein. Okay, and here I'm thinking of an ethereal ring where the inject dimension of R from left and right is finite. And recently, due to Ricard, we have a new notion about inject generation for R. And Gorenstein rings, Gorenstein algebras are satisfy this. So, and Ricard proved that if injectives generate for R, then the finitistic dimension of R is finite. So this is due to Ricard. and here R has to be finite dimensional algebra, right? So I'm not really precise for the various different assumptions, but somehow we have like a sequence of nice applications between all these different well-known notions for rings and algebras. Okay, so the idea is, so here inject generation, right, means that what it means is that you want to generate the derived category of R by the injective. So you want the localizing subcategory generated by injectives to be the whole derived category. And Ricard proved that the finitistic dimension of R for a finite dimensional algebra is finite. And this is the big finitistic dimension. So maybe I can recall this. So what is this? This is, I'm considering the project dimension of modules which they have finite project dimension and X is in mod R. So this is usually called big finitistic dimension, and the finitistic dimension conjecture asserts that this dimension is finite. Okay. So there was a very interesting relation between properties of the derived category with certain homological properties of your algebra, right? This well-known finitistic dimension conjecture. Okay, so what is really useful here and a well-known fact, so I put this on the left. So sorry, as I said to Rudradip, I have prepared a Beamer file, so whatever I'm writing, it's much better written in a Beamer file that I will send late after my talk, okay? Okay, so some standard fact that we know is that if we assume R and S such that the derived categories are equivalent, so then we know well that the one ring has finite global dimension if and only if the other ring has finite global dimension. So the finiteness of the global dimension is really a property of the derived category, right? And the idea is, what we would like to propose today is that we would like to formulate all the previous homological dimensions that we saw intrinsically for triangulated categories. So we would like to know that whenever you have two triangulated categories which are equivalent, then the one holds for the one category if and only if it holds for the other. So the aim is to formulate the above, say, homological notions intrinsically for triangulated categories. Okay, and let me go back. So if this sequence of diagram is, I call it star, then if this makes sense, then for sure I would like to show star for triangulated categories via certain intrinsic subcategories. Okay, so the goal of this talk today is to show you that this is indeed the case. We can do that, and we can develop such a theory. And the main idea is to introduce these faraway subcategories. Okay, so our approach focus on this new, let's say, distinguished, intrinsically defined subcategories, and this is the main new tool. Okay, and we would like to examine all these properties for triangulated categories, but not only for the derived category of the ring. So we would like to examine these homological categories also from the homotopy of injectives, for instance, or from the big singularity category, the homotopy of acyclics of injectives. And we'll see this at the end. Okay, so this is the basically the motivation. So we have this sequence of applications that I will return at the end of the talk. And I would like to see this picture in the world of triangulated categories, but with some new definitions that are coming from this nice distinguished intrinsically defined subcategories. Okay. Okay, so I can start the second part. So this is faraway orthogonality. Okay, so let me start by defining. So let T be a triangulated category, and given maybe better if I write small, given x and y in T, we write hom T x, y, this large greater, sufficiently large greater. This is 0 means that there is an integer n such that for all n greater than this, we have that the hom T x, y shifted by n is 0. Okay. Okay, and we can define similarly. We define what it means hom T x, y being 0. Okay, so this is sufficiently large and sufficiently small integers. Okay, and let's write x for a class of objects in T, and now we will write x right perp with this notation for all objects in T, such that for all x in this class, we have this hom vanishing. Okay, so different objects in this subcategory, so they have different n. So you may want to put n with a script here x in order to remember that the vanishing is different. Okay. Similarly, we have now is this symbol, so it's again the same for all x in x, hom T x T. Oh, sorry, is 0. I know. That's good. Okay. So this is what we call far away right orthogonal, and far away right orthogonal but smaller and smaller. And similarly, we can do this from the left. I'm not going to write similarly. We define this, and similarly we define this. Okay. So these are the orthogonal subcategories that will appear in this talk. Okay. So the main point is this, that I'm writing this when you can find an integer so that you have this vanishing. Okay. Okay. And now, so just remember these classes, because now I'm going to introduce another mysterious symbol for the intersection of this. So we write, if you have a better suggestion, please let me know after. For this intersection, And if we also write for this. Okay. Okay, so we have this for a class of objects we defined this again these subcategories, okay, and now we also consider the intersection of them, okay. So here, I mean, you can realize that if you are thinking in terms, say, of torsion pairs, these are, for instance, fact. If I write like a question mark for one of the symbols, for instance, I wrote this, and then I wrote also this. Then, of course, we have that x, if you have this, say, right, and then you get back the x right perp, and similarly from the left, okay? So you get the standard properties. Okay, now, so sometimes, and we will see example after, these faraway orthogonal subcategories will come in pairs. So these faraway subcategories will come in pairs. Okay, and what we mean by this, let me write as a definition. So T is a triangulated category, and so a pair x comma y of subcategories is called a far away pair if you recover y by the right perp, this symbol of x, and the same is true from the other side. Okay. And moreover, a triple of subcategories x, y, z of subcategories in T is called a far away now triple, as you can imagine, if x and y, comma y, and yz are far away pairs. Okay, so we'll see in a bit that we can really get examples of such say orthogonal pairs. Okay. Okay. Soon examples via silting theory. Okay. Okay. Now the point is that with all this notation that we have introduced, so let me go back. So what is this? So we have this right, left, faraway orthogonality. Okay, also from the left-hand side. And then what we did, we took the intersection of these categories. Okay, and we also introduced this notion of faraway pairs that we'll see examples. Okay, so okay, now comes the main definitions. Maybe it's better if I change page. Okay, and now with this setup, I'm going to define all like a sequence of subcategories, where from these subcategories I will define all the notions that appeared in the first part of the talk for triangulated categories. So main definition. So T is a triangulated category. So yeah, there are quite many. I mean, I can write basically all of them to see. So we define the subcategory of bounded bounded above objects, and this denoted by T minus, and this is what? This is TC, and I'm taking this right. So by TC, right? Sorry, I forgot. TC is the subcategory of compact objects. Okay, and the first definition is that what I call bound above object is a subcategory of which you get like this exactly. So you take your compact objects and then you consider this right pair. Then we have the subcategory of bounded below objects. This will be T plus. And then, as you may guess, this is this. And now what I will call bounded objects. Bound below bounded objects. I will just take the intersection, and I'm denoting this by TB. This is the intersection of, and if we see the notation that we used before, this is this, right? And this is exactly T plus intersected with T minus. Okay. Sorry for that, but I'm going to introduce all the subcategories now. And so the subcategory of bounded above projective objects So what is this now? I'm taking, this is the notation T minus P. I consider TB, and then I'm taking this left pair. And I continue now with the subcategory of bounded below objects. I can write here. So this is T plus P. And again, I take TB.
We bounded below projectives.
Yeah, thanks. Okay. And I'm taking this left pair. Okay. And now what will be the bound projectives? It will be the intersection of the later two. Bounded projectives. Bound projective object. This is, so the notation is TBP, and this is the notation that we had before, and this is exactly the intersection of the previous two. Okay, and then we have, in the same spirit, we have bounded above injective, bound below injective, and bounded injective. So we have three more subcategories. I can write it for completeness. So the subcategory of bounded above injective objects. So what I'm considering here, so the notation is Ti minus, so I have Tb, and I'm taking the right faraway orthogonal. Then I have the subcategory of bounded below injective objects. So this is T minus plus. This is Ti plus, and I'm taking Tb. This is this perp. And then the bound injectives, subcategory of bounded injectives. So it's the notation is TIB, and this is TB. So the bound objects, right perp with this, which is the intersection of Ti plus intersect with Ti minus. Oof, okay, so it's a big list of definitions, which basically is what I told you is that I started to consider these faraway orthogonals for the compacts, and then I took intersection for the bound objects, and then for the bounded, I started to consider what it could mean bound above projective and bound below projective, and then similarly bound above injective and bound below injective. Okay. Okay, and then let's see, for the example of the derived category of a ring, what these subcategories mean, right? So if we need to recall something, I have the notes here. So the first example, is, so now T is the derived category of a ring. Of a ring R. Okay. Okay, so let me make, maybe it's better if I make a table, or okay, TC, T minus, T plus, TB, T minus P, TBP. Maybe there's not enough space here. Okay, we know very well what are the compact objects, KB small prods, finally generate projectives. Then T minus, you get what you expect, D minus of R. T plus, you get again what you expect. And now what is TB? The bound objects is dB of big mod R, right? I'm writing dBr. T minus P is K minus of big projectives. TBP is KB big prods. Okay, and there are two more that we can really compute, Ti plus and TIB. Okay, so what was Ti plus? Ti plus was, right, remember, Ti plus was this right faraway orthogonal of the bound objects, and we can really compute that Ti plus is K plus of big injectives and KB of injective R modules. Okay, so with this new subcategories, right? For any, with this definition, we really get for complexes for the derived category what we were supposed to get, right? So it looks that it really works well. Okay, and let me pass to a second example, which is what I promised, the connection with the silting theory. So let me briefly recall. So T is a triangulated category. So we take M an additive closed subcategory of T, and we say that M is silting if this pair greater than 0 and less recurrent. It's a T structure in T. Okay. And we know, moreover, M is tilting if it is silting, and moreover, from M to M different than 0, this is 0. And when an object is silting or tilting, if the additive closure of M is a silting subcategory. Okay, this is subcategory, and an object M in T is silting and tilting if, add of M is a silting subcategory. Okay, there's a nice remark here, a nice observation that I'm going to use, is that if you work over a compactly generated triangulated category and you have a silting object, then there is also a Cauchy structure associated with this silting object. So remark that now if T is compactly generated triangulated category, there is a Cauchy structure associated to a silting M. Namely, what is this? So we have, and we take homorthogonal. This is the left-hand side, and this is the Cauchy structure. And
Can you push the page a little bit?
is add of M, right? Yeah, sorry. With cohort add of M. So this is a result due to Lydia Angeler, Hugel, Frederick Marx, and George Vitoria. Marx, Vitoria. Okay. And here it's natural to consider what if the silting, if you have such a triangular category with a silting, what happens when you restrict to, for instance, to the subcategory of, for instance, to a subcategory. So questions. Sorry. So what I should have said before is that sorry. Where is it?
Could you please put this remark back on?
Yes.
And move it up a bit?
Yes.
Thanks.
Is it okay? So sorry, can you hear me? Oh.
Yeah, yes, thank you. Sorry, I muted myself.
No, but something happened here. Wait. Sorry, what do you see now?
Yeah, we can hear you and see the page. It's fine.
Okay. 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 Wait. Oh. Okay, for a while I could see only like lines here. Okay. Okay, so some basic questions here is that what we can examine is, for instance, okay, if you have a silted structure, does it restrict, for instance, question, does the silting structure restricts to this subcategory?
Can you bring the page down a little bit? No. Yeah, thank you.
And the main question is can we describe, and the main question is, can we describe the subcategories TBP, TB, TBI? So the idea is, do these subcategories form what I call a faraway triple? And here, the interesting thing is that under the presence of a silting module, a silting object, we get a nice relation between these subcategories, and the answer is given in the following result. So this is, as I said, together with Panagiotis, Kostas, and Jorge Vitoria. So if you have T, a compactly generated.
Can I just ask one question?
Yes.
So this question that you have written down on the page here, that if you are asking, does the tilting structure restrict to this M perp
Yes.
then Langle Wrangle? Is M perp Langle Wrangle a candidate category?
Yes, in this case, you can prove that this is a thick triangulated subcategory.
Oh, it's because it's tilting, right? Because it's tilting.
Yes.
Sorry. Cool.
No, thanks. Okay, and take M be a compact silting object which far away generates. So it has a generation property with respect to the way orthogonal subcategories. Then we have the far away triple. Okay. So in this case, so these three pairs of subcategories, they are indeed far away triple, but we can really describe what is TBP. This is the thick of M. In the middle, you get thick of the heart associated to M. And here, so what was TBI? So TBI was the bounded injective objects. Okay, and here we get thick of M star. Okay, and what is M star? So we are in the compactly generated triangulate category. So by M star, we denote the Brown combinates dual of M. Okay, and this triple of subcategories now has further properties. So we have a faraway triple such that so the T structure induced by M restricts to TB as a bounded structure. And moreover, the Coti structure, again induced by M, as we saw from the remark, also restricts now to TBP, and this again as a bounded Coti structure. And we have also M star. So the Cauchy structure induced by M star restricts to TBI, again as a bounded Cauchy structure. So in the presence of a compact silting object, we can really get an idea of what are these subcategories, right? And how they are related via this notion of a faraway triple, okay? And moreover, these pairs behave very well, the T structures of M and the Cauchy structure, with respect to restricting them to either TB or TBP and then TBI, okay? So in this case, where we have a compact silting object, we get this nice description of these faraway triples. Okay, so this was the connection with the silting part, and now let me move on to the homological part. So homological notions now for triangulated categories. Okay, so definition. T is a triangulated category, and we say that T is number one of finite global dimension. Okay, we denote it by like this. If the subcategory of TBP coincides exactly with the bound objects TB. We say that T is Gorenstein if TBP is exactly TBI. We say that T is generated by injectives if you can recover T by the smallest localized subcategory, but now from TIB. Okay? And TIB, remember, these are the bounded injector objects. And one more. So we say that T is of finitistic dimension. If you consider TIB and you take the right orthogonal, intersect with T plus, you ask this to be 0. Okay, so we have these definitions, but basically, probably for those that they are familiar with recent development of this, you have seen this before in Ricard's paper, and also Henning Krause has defined this finite dimension. And this notion, right, is different from the recent and very interesting paper of Biswas, Chen, Manali, and Parker and Zeng, right, of the other authors. Okay, so we have now these notions of finite global dimension, Gorenstein-ness, and generated by injectives, and you see that everything has been defined in terms of these subcategories. Okay?
Can I ask
and
a
then,
question?
Yes.
No, sorry, you go. Sorry, I stopped you mid-sentence.
Sorry?
I stopped you mid-sentence.
No, I'm going to write the result now. Maybe.
I was going to ask, in this case, is TBP always generating T?
No. In general.
In general, no, right?
No.
Yeah.
Okay. And then, as I said, what was the first motivation, right? Remember, what was the first motivation is to get this picture, right, for triangulated categories via this distinguish intrinsically defined subcategories. And this is indeed the case. So the theorem says that so let T be a compactly generated triangulated category. Then, so I leave some space on the left because I will return. So we have this, and this implies Gorenstein-ness. And this implies injective generation. Generated by injectives. And this gives also finitistic dimension of T is finite. Okay, so we really recover with this notion the first implication that we saw as a motivation. So one comment is here. I'm cheating a little bit because we need some further, some more conditions on the subcategory of TBI. Just some condition on TBI for this to be true. Okay, and what we are missing from this list of definition is the regularity. Okay, I leave some space here because I will return, and let me write what we define, what we write about regularity. So now we start T is a k-linear triangulated category, and X is a subcategory of T. So, and now we consider the following fixed subcategory of T. So again, a nice decoration for this right perp, which has this HF for homological finite. And this consists of all T in T, such that for all X in X, you ask the direct sum of this home space for all n to be a fan-generated K module. Okay. And now the bounded finite objects are, so now for X, we consider the compact objects, and we take TC, and we take this right perp, this homological finite. Okay, so we have this, what we consider here again is all objects in T, such that this direct sum, we want this to be fan generated over the K. Okay, and then what means regularity? So definition, a k-linear triangulated category T is said to be regular if TBC equals TC. Okay, so regularity. So here you really don't see the previous list of subcategories, but we can also define this. And about regularity, if you go back to the main theorem, then you can really put this here, T regular, and under certain conditions, we can prove both directions, right? Because you remember one direction we don't have due to Nagata example, so we have proper, again, this is true via certain conditions, but these conditions are in terms of the subcategories that we defined, okay? So, and then somehow the first picture is complete. So we really have all the sequence of implications that we would like to see in the setup of a compactly generated triangulated category via these distinguished intrinsically defined subcategories. Okay. Okay, and now what is also interesting is that we can also detect, as I said, regularity from different categories. So theorem. So let me make two tables, maybe it's better. So here is T, and here I'm asking TBC to be the same with TC, and this is the regularity that I have above. And here I put the derived category of a ring. And here I'm putting the homotopy of injectives of A. Now I'm changing my notation A. And here I'm
Sorry,
putting...
Chrysostomos, may I ask, I didn't get it. What was the TCB with the C at the bottom?
It's this bound finite objects.
Sorry. Yeah, okay, thank you.
Thanks. So this is the big singularity category. And here we can really recover the classical regularity where R is a commutative Noetherian ring. And here, the regularity, we get back that the global dimension of A is finite, but both from the homotopy of injective, but also from the big singularity category. Okay. And we can also prove the same. So remember what was the definition for finite global dimension, that TBP is exactly the bound objects. So here is the derived category. Here is the homotopy of injectives. Here is the homotopy of acyclics of injectives. Okay, and here we really get that the global dimension is finite. Again, the global dimension of A is finite, and the global dimension of A is finite. Okay, and for this table here, this is for any ring R. And here A is sorry, I forgot. And A is an Artin algebra. And both here A is an Artin algebra. Okay, and this is an interesting aspect of the theory that we suggest, right? That you can really detect these homological notions via the homotopy of injectives and via the big singularity category of the homotopy of acyclics of injectives. Okay, I still have like 6 minutes. Is it okay if I continue? Or...
Yes, please.
Yes, okay. And now let me pass to the last part, which was the applications. Okay, so far what we have seen is that basically with this list of subcategories, right? We got first of all this detection of regularity or of finite global dimension, of course, from the derived category, but also from the homotopy of injectives and from the big singularity category. And moreover, we also saw this this sequence of implications, right, where we really get what we probably we were expecting from the first page, from the motivation. Okay, and now let me pass let me now explain to you that via these subcategories we can also define what's the singularity of a triangulated category. So definition, the singularity category of T is defined TSG. So I'm taking TBC star TC, the compacts, and I kill out the intersection of these two. So this is the star subcategory. So this consists of all objects where you have a triangle, where the first term is here and the cone is here. And we suggest this quotient to be the singularity category, triangular category. And of course, in order to examine if this makes sense, right, we'll take an Noetherian ring. And T is the derived category. And then this TSG that we just defined above is the classical singularity category that we know. So we can really compute that here you get the bound complex of ungenerated modules over R, and this intersection is just the compact objects, the perfect complexes. So this is the singularity category.
Just 1 second. In this example, TBC is not dp mod R itself.
In this example,
In the Noetherian ring example, isn't TBC, maybe it is not, I'm asking you, is TBC dp small m mod R itself or not?
yes, in this example, yes.
Then when you are taking the Vitoria quotient.
No, wait. No. Yes, sorry, yes. No. No, it's not. So TBC, yeah.
No, but I mean when
because you really need to get the finally generated modules, and then sorry, what I wrote here. TBC.
Like TC equals TBC was the same as regularity. So TBC, I'm guessing, is db small m mod R.
Wait, there's a C missing here.
That makes sense. Sorry, thank you.
Okay, sorry. Now I understand.
Yeah, very good.
Okay, and then we can define this again via these subcategories that we have defined. And one application that we consider is in the setup of recollements of triangulated categories. So given a recollement x, t, y, so this is I, E, L, R, Q, P. So the question is, so what means recollement? So you have an adjoint triple here, you also have an adjoint triple here, this, and this are fully faithful, and the image of this guy is exactly the kernel. And the question is, okay, if I give you a recollement of triangulated categories, so when the singularity categories, when of T is equivalent with the singularity category of Y. And similarly, when the singularity category of T is equivalent with the singularity category of X. Okay, so two natural questions that have been considered in special cases before. Okay, and then using what we have done in this work with Jorge and Panagiotis, we can really prove easily the following result, which says that, so you have a recollement as above, x, t, y. So this is a recollement of compactly generated triangulated categories. And we assume you want some relation between the compacts of x and this xbc, right? That we saw before, the bound finite objects, and the same we want this for t and for y. then the following statements hold. So first of all, the functor I induces a triangle equivalence between the singularity category of X and the singularity category of T, if and only if Y is regular. Okay, so the regularity of this part, right? This, as you expect, gives that the singularity category of this is 0, and then it's like having a short exact sequence at the level of singularity categories, and this being regular implies that the singularity category of Y is 0, and then you get this equivalence. And moreover, for the right-hand side, so we can show that the functor E, this is via I, the functor E induces a triangle equivalence between the singularity categories if and only if X is regular, and here we need something more. We need the functor X to send compacts to compacts. Okay. So also, so with this sequence of definitions, also we get nicely this result also at the level of singularity categories for triangulated categories. Okay. And sorry, I'm over time. Thank you very much for your attention. I will stop here.
Thank you very much, Chrysostomos. Let's all give this big a round of applause. If you have any questions for the speaker, please ask them now.
So what you see now is again my paper?
Yes.
Okay. Now, okay.
Now we see you.
Okay, thanks.
I have okay, sorry, Lucas, yeah, please go ahead.
So I want to ask, is this notion of bounded above projective and so on, is this related to derived projectives?
No, yes, we haven't thought about this, Lucas. I thought
I mean,
at some point
you related it to silting objects.
Yes,
silting objects
yes,
are
yes.
derived projective, but in
yes,
general.
yes. I have, yeah, I thought that I should look at this at some point, but you are right. There should be some relation. You are right.
Thanks.
So there should be an inclusion one way, right? Your vulnerable projectives should be derived projectives, if not the other way around. I mean,
Yes,
you would expect something like that to be true, I'm guessing.
Yeah, probably, yes.
I had a question. So when you were setting up the triangulated formulation of Jeremy's result, so you said something more would be needed to show the implication of injective generation implying finite and finitistic dimension. So I'm guessing you also have a triangle in your proof there, and in the condition that you didn't mention, there's something extra. I'm guessing there should be a triangulated analog of like the tensoring with dA giving an equivalence between projectives and injectives, the way we have for finite dimensional algebras.
So this is about the subcategory TBI, right?
Mm-hmm.
So the condition that we need there is a condition about TBI, which is very natural when you work with the derived category, and you basically ask this subcategory to have a certain generation property for a class, for a set of objects, which also, and then you also ask this to be like closed under self-coproducts. So this is the tricky part. So you need some really nice properties for this TIB in order to prove this. And this is not so technical, but for the standard case of the derived category of rings, this is true.
Yeah, and being closed under self-coproducts was an important, I mean, in Jeremy's own setup, that was an important ingredient.
Yes.
So yeah, that makes sense. Thank you. Yeah, can I also say, like, there are, I mean, all these conjectures. So, for example, there was a paper by Yiping Chen and 3 other authors. I can't remember all of their names, where they looked at I think the Ostrander-Artin conjecture and whether it was singularity invariant. And the result that they obtained was that yes, if the equivalence was induced by like a 6-step ladder of adjoints or something, 6 or 5, I don't remember.
Yes.
So I'm guessing you can, I mean, without maybe a lot of extra effort, one can formulate those kinds of results where one looks at a conjecture and asks.
Yes. I think now that somehow there are at least our at least goal was that to check that these notions are the correct for this sequence of implications, and it was very, very interesting that we realized that this can really you can really get they really work nicely for the homotopy of injectives and for the big singular category that I really want to understand if there you have some intrinsic subcategory of all these homological notions via this subcategories that I define. And yeah, and this is happening. And yeah.
Can I also? Sorry, no, go ahead.
Sorry. May I ask a question?
Yeah, please go.
Okay. So Chrysostomos, on the first section that you spoke about silting, I have a couple of questions. If you have a triangulated category that does not have silting subcategories, can you actually, do you have examples of triangulated categories without silting subcategories that have these far away?
No, not that I know, Anastasia. I mean, we're happy enough to realize that at least in the silting case, where you have compact silting object, you can really understand this table of subcategories that we have been thinking, and then this form a nice pair of subcategories, and you can really describe as thick or the hard or the thick of the dual. So other than that, I don't think that we have any idea about.
No,
Because having a silting object kind of implies that all of your objects are close enough, in a sense, by Yama. So this is why I was asking, like, maybe there are more exotic examples.
But at least we have applied this to some certain classes of DG algebras where you can really see this theorem there in that it works. But of course, the silting is the algebra itself. So.
And another question, maybe I missed this part because my connection was not okay. What was faraway generates? Did you explain this?
Maybe not. Yeah, I also skipped that. So this is again a generation property with respect to the subcategories that you ask for the compacts now. It's like when you ask generation with respect to did I write it? No.
I think you didn't mention it.
Okay. Yeah, you want basically, for instance, TC to have such a description as a perp from such a faraway orthogonal. Okay, so it's such a generation property. It's not. It's a generation property really with respect to this orthogonality condition.
Okay.
Okay.
Thank you, and thank you for your talk.
Based on what Anastasia just asked, Chrysostomos, when you have a finite dimensional algebra that's of infinite global dimension, then DB, the boundary of category of finite degenerate modules, can't have a silting object, right? But isn't that an example where, despite there not being a silting object, you can still do all of these far away, take into this far away mechanism?
So in the case of DB small mod, you are saying?
DB small mod A, where A is of infinite global dimension, the category. Oh, no, it's about the big category having a certain.
Yes, exactly. So I don't know if I said this. So in most of the cases, you really need coproducts and products, right? So we are working with big categories. And then these subcategories give us, I mean, what is interesting most of the time is that you really want DB of big mod, or you may need KB of big prods, right? And now with these subcategories, you are able to get this and work with them via these definitions. And what is maybe and the regularity just needs this. It's a bit in a different, say, direction with respect to the definition that I gave earlier. But this also gives what you expect, because for the derived category, you get the regularity, and then you just have to think that, okay, this is an R linear triangulated category.
Yeah.
Or if you work with Artin algebras, then it's an R linear category. So it's still okay.
Shouldn't be asking about it. I'm sorry. Anybody else? Any other questions? Yeah, our notion of regularity and your notion of regularity coincides in some cases, but it's hard to, I mean, both can be called a general, not, yeah, it's hard to call any one the specialization or generalization of the other. Yeah, it's not, that's not true. But
I don't know. Yeah, I mean,
yeah, for DB,
I mean, here probably, I mean, you saw that I'm not using any like heavy machinery, right?
you're not using any completions, but still.
No completions, no such arguments. So it's basically really triangulate arguments, and what I find interesting is that these definitions, they are really working. So with no really heavy extra machinery.
Yeah.
But of course, as you said earlier, is that the idea is that you really want the big category, right? You really want complete and co-complete co-products and products. So
also, can I say, yeah,
yes.
sorry, go on.
Yeah, please.
Liran had a paper, I don't know if Liran is in the audience today, I did invite him, where he had a Gorenstein version of Jeremy's injective generation result. And I think you can do that with your setup as well.
So which paper you mean?
I'll send it to you.
Okay, thanks.
Yeah. Yeah. Maybe I can, yeah.
Okay, yeah, later.
Yeah, something by Liran Shaw, and it's the last, I mean, he has a Gorenstein version of records injective generation results. So if one can define Gorenstein projective objects or bounded below, bounded above, then bounded projective objects in this setup, one can do, and it's probably just a two-line exercise from what you have already shown us, but yeah.
Yeah.
Okay.
Yeah, thanks for listening, right? I mean,
any other
sorry for the interruption.